Okay. So chapter 12 coming up, exam next, due date next Monday. Of course, you can take it anytime you want. And then on that day, we'll jump into chapter 13, I think, is equilibrium. Yes. And I'm pretty sure by the time that one rolls around, the exam for equilibrium. Oh, we may be able to get that one into your average also for the midterms. More is better. Okay, so I think we're going to skip the first one. That first problem is a doozy. Now the method for using initial rates to construct the rate equation is not a problem with this one. It's a simple process. But then when you get down to the mechanisms, that's where it's really gets kind of squirrely. Because there's a lot of art in determining mechanisms. That's why you're given these two to choose from, not just to create one from whole cloth. But even then, the reasoning behind it, and I tried to stick to what I thought the authors wanted the reasoning to be, really isn't solid. And I'll say that because of this. When you look at a mechanism like this one, where you have two reactants, I think two reactants go in and give you these intermediates. And one of those intermediates reacts with another reactant, gives you another intermediate. That intermediate reacts with another. The slow step in there is the one that determines the rate and the rate law. So I would be inclined to pick this one, the third one, to base the rate law, simply because it's a termolecular mechanism. It's the step that's termolecular. And remember, termoleculars are almost impossible to, they're very slow, because the probability of getting three components together at the right energy and the right angle is astronomically high. So that's why I would have picked the third one, but the authors picked the first one as the slow step. And maybe that is, but it's not obvious from the question that that's the way you should go. So I'm inclined to skip that one, and we can use a different one to get to gain experience in using initial rates. There are several others in the review document, so I'm just going to skip one. And needless to say, I'm not going to give you something like that on the exam. That would be completely ludicrous. I mean, you could spend the whole exam on that one question and still not get it right. I could spend the whole exam on one like it and not get it right. So I'm just going to throw that one out. So what we'll do is we'll also skip number 2 for now. We'll come back to number 2 because that's an initial rates series of experiments to determine the rate law, and we need to do a little bit more build up to that process. So let's start with number 3. Yeah, let's go down to number 3, and I'm going to keep track of which ones I'm doing so I don't backtrack. Yeah, this is a good one. So let's do 3. All right, the rate expression for a particular reaction is this. Rate constant, and then you have whatever component A is times component B. So the order of A is first order, the order of B is second order. And just as a point of information, the overall order for the reaction is third order. 2 plus 1 is 3, right? At least it was last time I looked. So the question is, with that knowledge, and you know that B is going to be increased from 0.1 molar in one experiment to 0.3 molar in a second experiment, what effect does that have on the rate? So we're starting off here with 1 molar, and we're going to that. And you have to assume from the wording of the question that A remains constant. So whatever A happens to be, it stays A, whatever that concentration is. We're only changing B. So if this one increases from that to that, how many times, what's the multiplier factor for the rate? How many times will the rate for that one be? So many times would equal this. That's a bad choice. Let's say this is A and A. Okay, so you look at how many times did we increase B? We tripled it, right? It's times 3. But the effect on the rate is the square of that times. So 3 squared is 9. So the increase on the rate is 9 times. And remember in the PowerPoint slides, we went through one that basically compared 0 order, first order, and second order, all other things being equal, and we calculated the amount of the reactant that would be remaining. And as you increase the order, less of it is remaining after the same time period. So the interpretation there is that the higher the order, the faster the rate, because you have less left over, right? And this is just a confirmation of that. If you increase that amount 3 times, well, it's sort of a confirmation. I shouldn't say direct, sort of an indirect, backhanded compliment, because this second order means that you're 9 times the rate, instead of, if it were first order, like A would undergo the same change, then you would have only 3 times, and the rate would be 3 times as fast. That being said, what if we did change the amount of A from 0.1 to 0.3? At the same time we change B. What effect would that have on the rate? Well, this is 3 squared, and this is only 3, right? So 3 times 3 times 3 is what? 27. So we would increase the rate of the initial rate of the reaction 27 times if you tripled this one and you tripled that one. Okay? So that was number 3. And I'll check that one off. Okay, let's look at number 4. For which reaction order is the half-life of the reaction rate, the half-life of the reaction, proportional to 1 over K? Right. So let's look at what are the half-lives, right, for 0, first, and second order. Well, for 0 order, the half-life is, let's see, T 1/2 equals, and then it can be on down the line. So what's the formula for that one? Right? It's in your useful information. I'm gonna see if I can remember it. Initial concentration divided by 2K. I think that's right. That's not to say that these are equal. I shouldn't do that. Just say T1/2 is this one, or this one. How about 1? 0.693, I believe, over K. And the last one is 1 over 2 times. Excuse me, that's not right. K times. There we go. Now, if I'm wrong, somebody tell me. I'm working from memory. They're in the useful information. Okay. Okay. So now that we have this information, we can answer the question, which is, which of them are proportional to 1 over K? Well, let's take a closer look. How about this one? Is that proportional to 1 over K? Well, you remember how to factor things out of a fraction, out of an expression from your algebra class, right? This is the same thing as, correct? Right? Factor it out. This one would be like that. And this one's already set up for us. Each one is proportional to 1 over K, to the inverse of K. The half-life, that is. Okay. I didn't derive the half-lives. I could, and I may do it. I mean, if we have time today, to show you where the half-life expression comes from. I think that those documents that explain that are in Blackboard if you're interested. And you may have already looked at them. Okay, so that was number 4. So the answer to that one is all of the above, D. Let's see, how about 5? Oh yeah, that's basic stuff, right? If this reaction I think I need a fresh one here, yields H2 plus I2, yep, is second order, which of the following will yield a linear plot? Right? So remember how you tell if you've got a linear plot. You take your raw data, right? You've got time, you've got concentration of HI, right? And you have values here and you got values there. So next, what do? You take the natural log of that one. And then you take the inverse of that one, right? And then you plot that one, then you plot this one, then you plot that one. And the linear one, the linear plot with this on the x-axis and one of these on the y, the linear gives you the order, right? This is 0 order, this is first order, and this is second order, right? So it's simple. Which one of these, if it's second order, would give you a linear plot? That one. Plot the inverse. So that's why B is the answer. All right, that's 5. Let's see. Let's take a look at 6. Okay. Here we go. 6. We've got these two reactions. The overall reaction, of course. Well, I don't even have to write this one up on the board. We've got the overall reaction, then this proposed mechanism. All right. So, is this a valid mechanism? First of all, what's the first rule? You have to add up the elementary steps and get the overall equation, right? Hess's law. If you can't do that, then the mechanism is bogus. Throw it out. So let's check. All right, there's one C and there's another C. So there's your two C's. That R is on the right and that R is on the left. They cancel. And that's good because those are intermediates. They don't appear anywhere in the overall equation. And then you have B sub 2 right here, right? So what does that tell you also? That's a diatomic molecule, a diatomic element. And A2 is also a diatomic element. But there's two of them. There's one here and there's one here, right? So the first condition is met. Second condition is the overall rate is determined by the slowest elementary step. So which one is the slowest? They're both slow, right? But one of them's got to be slower than the other. And step 1 is the elementary step that is the rate determining step. So that's why the answer is B. Now we could do a lot more with this. Or we could write an expression for the rate equation based upon that one right there. But that's not the question. So we've answered the question and we're going to move on. Let's see. Let's come back to 7. You know, I think we need a little more elementary push before we get into before we get to this one. It's not that difficult, but I think we ought to build to it. So we'll come back to 7, and I'm marking them off so I know which ones I've skipped. All right, this is a good one. Right. We get into Arrhenius Law, right, having to do with the activation energy. So I do need to draw this one. So let's say 8 and 9 are going to be based upon this drawing. So let me put this up here first. Right. So this is the reaction progress. Just basically time. And this is the energy, right? And that's not defined here. The idea is that you recognize what we're talking about. I mean, you recognize the appearance, the general appearance of this graph shouldn't need identification of the axes. Now, of course, that flies in the face of everything I've been telling you about your reports, your lab reports, right? All graphs must stand alone, right? But this is an exam or an exam practice, and indulgences must be made. What we're trying to do is see if you recognize the appearance of this graph. So that's progress, and this is energy. Right? So if we start here with reactants, and we end up over here with products, right? So we have so much energy here in the reactants, and we have so much energy here in the products now. We know it's an endothermic reaction because you have more energy stored in the products. You put energy in, but you didn't get all of it back. Right? And then in between there, we have this series of steps that goes like that. Okay? Maybe I drew that a little high. Doesn't leave me much room for notations. Let's bring it down just a little bit like that. There we go. Okay. We've also added another feature. Right there. And now we're going to draw some lines and label them. Right? So between here, the energy between here and here is A. Right? So from there to there, right, is A. B is between here and here. Okay. C is from here all the way to the top. Okay. D is between here and here. And E is between here and here. Okay, I think I got all my letters in there. All right. What do these things mean? Some of them are true, but they're just not very useful. We already talked about this one. That's basically the enthalpy of the reaction. Okay. This one is the energy. B is the energy of the reactants at the start. Okay. A, what is A? A is the amount of energy required to get the reactants to an activated complex or transition state. Remember, once they get to that transition state, they can go two ways. If they're right on the value, then they can either go to the right or the left. Now, one thing to recognize is in a reaction mixture, when you've raised the temperature to a certain point, every molecule and every atom in that mixture doesn't have the same energy. It's an average energy, a weighted average. It's a, oh, my mind's gone blank. It's a root mean square. That's what I'm looking for. It's the root mean square average energy. So you look at this in terms of individual reactants. When they reach this point, then they can go over it. Some of them are in that mixture, have a lot more energy, so they just go right over the top. And some of them don't have enough energy. They go whoop and back down. But for individual reactants, when they reach that point, if they have just that amount of energy, they need just a little bit more bump to go over the other side. That's the transition state, and this is the activation energy, E sub A, okay, for the uncatalyzed reaction. Okay. So which line represents the catalyzed reaction? By the way, that's the answer. A is the answer for number 8. Number 9 is the catalyzed reaction. All right, what's the activation energy for the catalyzed reaction? It's this dotted line. The catalyzed reaction lowers the activation energy. How does it do that? Well, it provides an alternate mechanism. It's not the same mechanism as the uncatalyzed reaction. So you would have different elementary steps in a catalyzed reaction. and it takes less energy. So what does that mean to the overall? That means that for individuals at this point, right, they don't have to go to the top. Like, by an alternate mechanism, they reach this point, and now they're products. Let's see, what else have we got? Well, this is the catalyzed, which would be number 9E. Okay, that's the catalyzed activation energy. The rest of them really aren't important, so we'll move on from there. Okay, let's see. Okay, let's do number 10. Since we're on the topic of catalysts. Right. Remember we talked about the homogeneous versus heterogeneous catalysts. And the basic condition for homogeneous catalysts is that they exist in the same phase as the reactants. So, based on everything that's given in this question, the reaction of hydrogen peroxide to yield water and oxygen, when it's catalyzed, it has this mechanism. At least that's a proposed mechanism. And you saw the picture, right? The little video on our during the lecture of elephant's toothpaste was basically an iodide catalyzed decomposition of hydrogen peroxide with a few added ingredients for effect. So, and you remember that the hydrogen peroxide was liquid, and they added some food coloring and some Dawn, but they also added, at the last second, a little test tube of liquid that was actually dissolved potassium iodide. So they're both in the same phase. Hydrogen peroxide is dissolved in water. Potassium iodide is dissolved in water. You put them together, and you have a homogeneous catalyst. Well, that being said, this is what the mechanism looks like. One proposed mechanism. Notice that whenever you see a mechanism, and that's the only place that you're going to see the catalyst. The overall reaction will not have the catalyst in the equation. Usually if we write something like that, we would have this. This is number 10. And it would yield 2 waters and 1 oxygen. But in that form, if you had a catalyst added to it, this says there's no catalyst. But if we write it like that and we put this, we're saying that that's a catalyst, or it's an added ingredient that's necessary for the reaction to proceed, as described further below the equation. Or if you have the mechanism, then you can identify the catalyst in the mechanism. What you look for is in one step, a component goes in, and then in a subsequent step, the second, third, fourth, however many there are, at some point, that substance is reconstituted unchanged, or at least macroscopically unchanged. So that iodide went in here and it came out there. Right? So it was intimately involved in the reaction, but it was not consumed by the reaction. Okay, so that being said, the iodide ion is the catalyst in this reaction. That's why B is the answer. Okay, that was 10. There are other types of catalysts, right? Heterogeneous catalysts are different phases. And we talked about that in class. Let's see. 11 is a little off the wall, and it take a lot of time to do 11 because you have to determine you have to actually plot the data to get 11. So that's something that you do as more or less homework. It's not something that you would get in an exam. Unless you had a professor that would give you an exam that only had one question. And sad to say, I've been subjected to that. Like a final exam with one question. And you got to know how to do each of the steps all the way to the end to get the right answer. And if you mess up anywhere in between, you get the wrong answer. So, although I will give my instructor credit, they usually offer partial credit along the way. Like if you did something right here and here and here, and you did something wrong there, getting the final answer was not the whole story. Okay, but I'm going to skip that one. That's this one, number 11. We're going to go down and take a look. Let me see. Do I want to do that one? Let me skip 12. Let's come back to 12. That requires a little extra manipulation. 13 is fairly easily explained. I mean, it looks like a lot, but it's really not. So for 13, we have this similar reaction we saw earlier. 2A sub 2 plus B sub 2 yields 2C. And there's your mechanisms. Okay? So the question is, according to the collision theory, right? Remember, the collision theory says that in order for a reaction to occur, there must be a collision between reactants. They have to come together. And not only that, they have to come together with sufficient energy to reach an activated complex state. In other words, they have to start breaking bonds and start reforming bonds in the process. And that also requires one other condition. They have to be oriented correctly. So no matter how much energy they have, if they come together the wrong way, that complex is not going to form. So what would the complex look like? Well, if the very slow step is the rate determining step, then we need to look at A sub 2 and B sub 2. What are they doing? Right? If they determine the rate of the reaction, then what would the activated complex? Let's see, where's my annotation? What would the activated complex look like? All right. Well, let's see. Oop, wrong. It's not going to let me do that. Okay, so much for annotation. Let me give my mouse back. There we go. So these are our possibilities. And notice one of the artifacts of using images as answers in a Microsoft Word list is that this may be the A subcategory of 13. But if you put a picture in there, it's going to be justified at the bottom of the picture. Right? So A refers to this one right here, and B refers to the one above it, like that. Okay, just so there's no confusion. All right, so which one of these are least probable? Well, anything that has a product or an intermediate in it can't be right, because you're still in an activated complex step. You haven't gone over the hump yet. You're not producing an intermediate. You're not producing a product, which is R or C. So R and C cannot be part of the activated complex. It's got to be A and B only, right? So that lets this A out. B looks like a good candidate, right? There's the diatomic A and the diatomic B starting to form bonds here and breaking bonds here, right? So why do I say that? Well, if it's diatomic, there's strong bonds between each A and between each B, but what are you going to end up with? Well, you're going to end up with a combination of A and B, right? It's going to look like when this one comes together with this one, right? That's before the collision. Then after the collision, that starts to break, and that starts to form. And once these break completely, then what you have is AB and AB, which in my mind could be R, or one of them could be C. Who knows, right? This is purely hypothetical. But as far as the question goes, the activated complex has to be AA and BB, right? You can't have an R there. That's an intermediate, right? You can't have an R there. You can't have a C there because that's a product, right? The only one that fits is the AA and BB. So the answer is B. This is just a reminder of what I think I mentioned in the lecture part of the class, is that you introduce to topics with the lecture and the PowerPoints and all that stuff, but you really don't know chemistry until you work problems. You're confronted with the application of what you learned in the lecture. Until you do that, you don't know chemistry. You've been introduced to it. That's it. That's why these review documents, these problems that we work through, are so critical to understanding chemistry. All right, let me check that one off. And, oh, this is a good one. Give us a slight breather. Which one of the following statements about enzymes is incorrect? Right, so it looks like all of these are correct. Maybe they are. If that's the case, then there are no incorrect ones. But if E is false, then there should be at least one incorrect one. So that means we've got to look at each one. So first of all, what is an enzyme? Well, one definition is that enzymes are biological catalysts. And in a very limited sense, that's true. They do speed up reactions, just like an inorganic catalyst would do. But they're much, much more than that. Catalysts, enzymes, the most of them, 99% of them, maybe 95%, are proteins. There are a few that are nucleic acid based, let's say, like RNAs, DNAs, that type of thing. But those are rare. Most of them are proteins. And what they do is they offer an alternate pathway for reactants in a cell to come together and produce products. And That being said, they are catalysts. They provide that alternate pathway, but they're much more than that, because enzymes are active. That is, an enzyme can be active or it can be inactive. And if it's inactive, it won't work, right? And the cell is under control. It controls that activation. And by doing that, it controls the reaction itself by making an enzyme active or inactive. It also, the cell also has, for some enzymes, minute control on how active the enzyme is, right? It can change it from this rate of reaction to this rate of reaction. And most biochemical reactions in the cell are like any chemical reaction. They have forward and reverse possibilities. Well, suppose the cell doesn't want to reverse. Well, it uses an enzyme that only works in one direction, and it limits the return reaction, right? Then if it needs the return reaction, it uses a different enzyme. Okay, so let's look at that being said, let's look at the possibilities and see which ones might be correct and incorrect. Okay, enzymes are proteins that catalyze specific biological reactions. For the most part, that's true. I mentioned exceptions to the rule, but in general, that's true. They are proteins and they catalyze biological reactions. Several hundred are now known. Actually, it's a lot more than that. When this question was devised, that was true. Several hundred. And that's true if you think of hundreds in terms of tens of hundreds, right? Thousands. So we can say A and B are essentially true. The molecules they react with are called substrates. That's true. That's particular to biochemistry. When you're talking about a reaction, rather than reactants, which we reserve for discussions of inorganic chemistry and organic chemistry, but biochemists prefer substrate as their reaction label. So A, B, and C are all true. D, they are equal to inorganic catalysts in efficiency. That is false. In fact, they are far superior to inorganic catalysts in efficiency. They have very, very high efficiency. When an enzyme is active, it is in the upper 80s and 90% efficient. They are very efficient catalysts. Whereas inorganic catalysts, you're lucky if you get 5% efficiency out of an inorganic catalyst. Okay, so D is really the only one that's incorrect. A, B, and C are essentially correct with some exceptions. All right, that's 14. Let's see, what do we got coming up? We might come back to 15. I'll probably use a simpler one than that too, to do the method of initial rates, because that's what that's all about. So let's skip that one for now and go to this one, number 16. Okay, so what are we given and what's the question? We're given this generic equation, and the initial concentration of A0, is 4.2 molar. And then we're given the first 2 half-lives. So what that means is the first half-life acts upon the initial concentration, and it lasts for 56 minutes. The second half-life starts with a different A0 that is the product of the first one. Right? So let's put that on the board in a form that makes more sense. If we were watching the reaction over time, then this is what we would see. We would have the A concentration here. We would start at 4.2 molar, and the time would be 0. Okay? So the first half-life lasts 56 minutes. And that means you would only have 2.1 molar remaining. Right? Half of it disappeared in that amount of time. The second half-life takes 28 minutes. So the second half-life takes 28 minutes, and it goes from 2.1 to 1.05 molar. Half of that one. Half of this one for that amount of time. So what's the overall time? The overall time would be this one plus this one, right? So that's the data that we're actually given. And we're asked to calculate the K. Right? So how do we do the K? Well, we can use half-lives, right? Each half-life has a K in it. We looked at that earlier. Each half-life, whichever, if it's 0 order or first order or second order, the K is the inverse proportion to the half-life. But we've got to decide which one is which, right? Because you can't calculate K based on the half-life if you're using the wrong order, right? Because they're 3 different equations. So let's put the equations over here on this side. So if it's 0 order, we would have the half-life would be equal to over 2K. All right. First order, the T1 half would be 0.693 over K. And second order, first, second, would be T1 half is equal to 1 over K times A0. Okay. So if you can eliminate one of those, then it would simplify things, wouldn't it? Would it be possible to eliminate one of these? Right? Notice this one's proportional to A0 and this one's proportional to A0, or the inverse of A0. This one, it doesn't matter. Right? The half-life does not change with concentration. So look at your data. If the concentration is here, you get that half-life. If the concentration is less, you get that half-life. The half-life does depend upon the concentration, the initial concentration. So that means first order's out, right? It doesn't work because it's not proportional to concentration at all. So we can get rid of the first order. There's no possibility. All right, so let's move, let's put second order over here. So we can do some calculations. So T1 half then is equal to 1 over K times A0. There we go. So now we'll do our, so what we're going to do now is say, all right, K is a constant, right? For this reaction at a given temperature, K will not change over any of these concentrations. K is always the same for under these conditions. So if we calculate K using half-life, calculate K for that one and K for this one. And if the K's are different, throw that one out, right? Because the K can't change. And the one where the K is the same for both half-life calculations, that's the one. And if we do that, then we'll already have the K right here, because that's the question. What's the K? So we'll just do those two calculations and see which one fits. And that's our K. All right? So how about this one? For zero order, A0 for the first one, T1/2 for the first one is equal to 4.2. Well, actually, T1/2 is a value. T1/2 is 56. 4.2 over 2K. All right? So you know how to solve for K. K needs to be over here. So we move it over there, put the 56 over here, right? So we just say K is equal to 4.2 over 2 times 56. And let's see what that value is. Let's see, 3.75 times 10 to the minus 2. 3.75 times 10 to the minus 2. Okay. All right, let's look at the other one. So the other one will be 28 minutes. And it's a different starting concentration, 2.1 over 2 K. So K is equal to 2.1 over 2 times 28. Let's see what that one is. 2.1, 2 divided 28. 3.75 times 10 to the minus 2. Those K's are equal. Now, logic would have it that you can't have both. You can't have, it can't be zero order and second order. So you can stop there. You got your answer, right? And that's why the answer is C. Rounding error, 3.7 times 10 to the minus 2. Pick the best answer. But if we did that calculation, we'd find out that the K for this one for one half-life is different than the K for the other half-life. And we can save time. And that's what you'd want to do on a test. I mean, once you got the right answer, just stop. Pick the right answer and move on. But that's the basic reasoning. The K is the same under both situations if it's zero order. All right, let me just take a quick look and see if anybody else showed up. Let's see one. No. Everybody's the same as it was before. Okay, so that was, excuse me, 16. And let's see here. All right, let's go to 20. Since we're talking about half-lives, let's move on to 20 and keep our stream of consciousness going in the right direction. And we'll come back to these other guys. There we go, there's 20. All right. And let's make room. There. And there. Let's see if I'm still centered. It's walking on me. There we go. That's better. Oh, I see the problem. I got too much junk on the floor over here. There we go. Different project. Okay. Number 20. So what are we dealing with here? We just read through the question and then read through the problem and find the question. First order decomposition of hydrogen peroxide at minus 30 degrees Celsius occurs with a half-life of 42 seconds. What will be the residual concentration of 10.2 molar hydrogen peroxide after 3 minutes? All right. So, look at the question. What will be the residual concentration? That tells me that we're not dealing with the differential rate law. We're dealing with the integrated rate law, because the integrated rate law has both the initial and the final concentration of a reaction with the time interval included. So that's why we need to find what's the order of the reaction and then write the integrated rate law so that we can plug in values and find the answer. So let's see what we're given. First order decomposition, right off the bat we're given. First order decomposition, 20. So it's first order, right? What does that mean for our our integrated rate law? It's going to be the natural log, is it not? So natural log of minus KT plus, well, I shouldn't do that because we have a defined reactant, don't we? H2O2 and H2O2. There you go. So that would be the form of our first order decomposition of hydrogen peroxide. The temperature is irrelevant because we're given the data and the temperature is not changing. That's just blue smoke. The half-life for this reaction is 42 seconds. Right? So the half-life equation for this one is T1 half equals 0.693 over K. Right? First order is independent of the concentration. Right? So that's why they can say half-life is 42 seconds and doesn't matter what the concentration is. Right? Otherwise, if it was zero order or second order, then this half-life would be useless because we don't know what the starting concentration is. Well, we could say 10.2. Right, we could use that as our starting concentration. All right, so that would take a small jump to get to that point. And we could say if we had a zero order or a second order, then we could use this as our starting concentration, which we would apply to this half-life, right? Because the half-life depends upon the concentration. All right. But it's first order, and we can solve for K now. Okay. So this is 42 seconds equals 0.693 K. So K is 0.693 divided by 42. (1.65 times 10 to the minus 2). And that would be reciprocal seconds, right? Because this seconds came over here. which puts it in the denominator, and that makes it to the -1. All right, if you're interested in units, those are the units for this K. All right, so now we can write our equation. Minus 1.65 times 10 to the -2 T plus okay. Now we're going to solve for that value. Now that we have our equation with our K value, then we just need a time. All right, so if we start off with 10.2 moles per liter, okay, and we have time, let's see, minus 1.65 times 10 to the -2 times T. But what's T? 3 minutes. And what are the units on K? Reciprocal seconds. T needs to be in terms of seconds, right? You have to match your units. 3 times 60 is 180. Right? This is reciprocal seconds. So they cancel. And then we have this one is our unknown. So we just need to solve. So let's resolve this one. The natural log of 10.2, how about that? Is 2.322. Well, I'll just write it out here. 2.322, okay? And then this one is times 180, change the sign, is minus 2.97, minus 2.97. And that's equal to the log of the hydrogen peroxide concentration. So let's add these together. So it looks like it's going to be a negative number, because that one's bigger than the other one. Minus 0.6476. And this is the natural log. Okay? All right. Now, how do you resolve that log? The definition of log is how you do it. The definition of log of a number, this number here is the power of the base. So this base is E. So E to that power is this value. All right, so on your calculator, you look for, well, on my calculator, it's not set up that way. It says natural log, and then the shift or the function change is to the common log. But right next door to it is e to the x. That's the one you're looking for. E to the x would be e to this power. So all I have to do on my calculator, since it's already there, I just press my e to the x button, and voila, 0.523. Molar. So the concentration of hydrogen peroxide after 3 minutes, starting with that concentration and this K value, at that temperature, we would have this much left. That's really a pretty high concentration. I wouldn't want to spill any of that stuff on my hand or splash it on my face. If we had time, we could calculate what that was in terms of percent composition. Let's see, 3% is on your medicine cabinet shelf. 30%, I've seen 35, 37%. That's concentrated that you would use for the elephant's toothpaste. And we could figure out, we could take the molarity and figure, I'm not sure what that percent means. Is that mass per volume? Probably. It's probably mass per volume. Anyway, that's 20. And that means the answer is B. Okay? So this is B. All right. So let me see. Is it time to backtrack? Yep. Time to go backwards. Let's see. Let's go right back up to 19. Here we go. All right. So I want to keep myself on track. I don't want to waste any time. Okay. Just checking myself. All right. So let me erase this and make room for number 19. All right. So let me see. I think 19 might need some space. So I'm going to start over here on the left, assuming I'm still on screen. Yeah. 19. All right. So what kind of problem is 19? For the second order reaction, nitrogen monoxide plus ozone yields nitrogen dioxide plus diatomic oxygen. The rate constant has been measured to be 1.08 times 10 to the 7th. Molarity, reciprocal molarity, reciprocal seconds at 298 K. And the activation energy has been measured to be 11.4 kilojoules per mole over the temperature range from 195 to 304. Right, so we're within that range. That means that the activation energy is virtually constant for that temperature range. What's the rate constant at 233 K? And there's your universal gas constant. You're going to need that. Why? Because we're going to use Arrhenius. Right? Now, which Arrhenius? Do we need the differential or the integrated rate law? Not rate law. Differential or integrated Arrhenius equation. Well, we've got two different temperatures. And we've got two different K values. So we need to use the integrated version. Right? So the integrated version of the Arrhenius equation says that the, I'll put it up here, the natural log of is equal to the activation energy divided by the gas constant. And then you have, is it minus or plus? Minus. There you go. So, K1 is at the lower temperature, K2 is at the higher temperature. So there's your higher temperature, there's your lower temperature. These temperatures have to be in K, right? Why? Because the rate constant is in K. I mean, the universal gas constant is in K. And we have to have moles, and we have to have joules, right? The universal gas constant is in terms of joules, not kilojoules. Right? So this kilojoules has to be converted to joules. So the rate constant, E sub A, is given as 11.4 kilojoules per mole. So we need it in terms of joules, 11,400 joules per mole. All right, got to get all of our values in the same units. So the higher temperature is equal to, let's see, 233. No. Higher temperature is 298. And the lower temperature is 233. All right. I like to put things up here on the board extracted from the word problem, because word problems, well, I've said it before, they're specifically designed to confuse. So you extract your information up here in a logical position so that you can see what you've actually got. So there's the high temperature, there's the low temperature, and the K that's assigned to each one is what? Well, we're solving for one of them. What's the rate constant for 233, right? That's unknown. But we do know the rate constant for the first one, 1.08 times 10 to the 7th. And I'm going to leave out the units for space. If you paid attention and made sure that all of your units match, then you won't need the units for the K. Okay, so now that we've identified which one's which one's associated with which one, then you can plug them in your equation, right? So the natural log of K2, 1.08 times 10 to the 7th over K1, K1, is equal to 11,400. I'm going to leave the units out here just for convenience. 3145. 3145. And then the temperatures, the T1 is 233. And then the T2 is 298. There you go. Now, the thinking part is done. The rest is crunching numbers. So if we take the reciprocal of this and subtract the reciprocal of that one, that'd be a good place to start, right? PEMDAS parentheses first. So 233, and you got a reciprocal button here. And then 298, another reciprocal button, and subtract. So we get 9.361 times 10 to the minus 4th. That's resolved here. That. And then this times that divided by that would give us the right-hand side of the equation. Okay, so I got 1.2835. 1.2835. Right? Now let's look at the left-hand side. What do you do with a log expression like that? How do you resolve that? How do you get the K out of that thing? Well, you need to remember, hopefully you remember from algebra, what do you do with logs when you have a quotient? The log of a quotient is the same as the log of the numerator minus the log of the denominator. So we would have a log of 1.08 times 10 to the 7th minus the log of K1. All right. So we're going to take the log of this one and subtract it from that side, right? Whatever the sign, doesn't matter. Change the sign, put it over here, and put them together. So what's the log of 1.08? And 10 to the 7th. Right? 1.6195. It's a positive number. 1.6195. So let's just go ahead and subtract that one. It's still in my, oops, about to make a boo-boo. I pay attention to my calculator. 16.195. So that's a negative. Change the sign, and let me see what if the other one's close. No, the other one's not close. I just punch it in 1.2835. Yes. Okay, minus 14.912. Yeah. 14.912. Yeah. Okay, and this side is negative log K1. So we just need to get rid of the negative signs, and then that would be the power of E. Right? So both sides are negative. Now they're positive. And K1 is equal to E to the 14.912 power. .99 times 10 to the 6th. Okay, that's your new K. If I did it right. Yeah. Well, at least there's an answer there that matches that one. And the key says it's right. Okay. I know that's a lot of work, but practice. That's your new K. Notice that the K at the lower temperature is here, is smaller than K at the higher temperature. Right? So the rate constant has decreased. And you would expect with a decrease in temperature, the rate of the reaction should also decrease. And that's what it has done. Now, what's the difference here in temperature? We've decreased the temperature by 63 degrees, which is 6 times. So it'd be 2 to the 6th. Let's see, where is it? Here it is. 64. So we would expect our rule of thumb, right? For every 10 degrees, you cut the rate in half. Then I would expect 64 to be near the ratio of this one to that one. So I'm just curious. So let's take this one, 1.08 exponent 7, and then divide it by that one. It's only 36 times, right? So the rule of thumb doesn't work here, right? Why? Because that has to be a specific value that we calculated in class in order for that rule of thumb to work. 10-degree change either up doubles the reaction or cut in half if you go down 10 degrees. So in this case, it doesn't work because the E sub A is not that value that we calculated in class. It's a different value altogether. Right. All right. So enough said about that. That's 19. Now we can go back to, let's see. All right, 18 is along the same lines. Let's see, 10. Yeah, we got time. Got an hour and a half left. So let's, while our minds are working that way, let's go back to 18 and analyze this problem. It's still an Arrhenius problem, right? Reaction rate and all that other stuff. But it approaches it a different way. And it's always good to work problems that are, right, the theory is the same, or the law, in fact, Arrhenius Law, is the same, but we approach it a different way. So we see it a different way. And that's how you gain confidence in chemistry, is to work different problems based on the same theories. Or law, as the case may be. Oh, I should have left that up there. We're going to need the Arrhenius equation. Well, actually, we're not going to need that one. I'll explain in a second. Okay. All right. Let's see, I'm dropping paper everywhere. We're back to 18. Yeah, actually, we are going to use that one. I shouldn't have erased it. I'm going to write it again. So this is number 18. And the integrated rate law for Arrhenius. Now, why would we use that one? Well, let's look at the problem first, right? Before we jump off on in a direction that doesn't have anything to do with the problem yet. If the temperature changed to 310 K, the rate constant K would change. Hold on a second. We have to, excuse me. We need more information. This is the beginning of the problem. The rate constant K for a reaction shown below here is 2.6 times 10 to the minus 8 liters per mole per second, which is molar per second, when the reaction proceeds at 300 K. And the activation energy is 98,000 joules per mole. So they've already changed it and given you the activation energy in joules to be consistent with the universal gas constant. Then the problem is, if we change the temperature from 300 to 310, the rate constant would change, right? I mean, that's axiomatic. What we're looking for is the ratio of the K values at these two different temperatures and estimated to the nearest whole number, right? Okay, so now let's say which Arrhenius equation are we going to need? Well, the one that has a ratio of K2 to K1, and that's the integrated one. Okay, so we have E sub A over R. And then we have, 1 over T1 minus 1 over T2, right? So if the high temperature is 310, what's the K? Do we even need the K? The question asks for the ratio, right? What's the ratio of the two, right? We don't even need the K. All we need is that ratio. That is our unknown right there, that ratio. So the initial temperature is 300 K. Final is K is there. E sub A is 98,000, right? 98,000 divided by 8.314. And then this would be 1 over 300 minus 1 over 310. Right? So that's that side of the equation. This side of the equation is just as it is. We want to solve for that. Right? So we resolve this side, gives us a number. So we take this one, 300 reciprocal, and then subtract 310 reciprocal. And we get 1.075 times 10 to the minus 4. Then that one times this one divided by that one. Nope, I messed up. I'll have to punch the numbers in. Okay, now 98,000 and 8.314. So this is 1.267 is equal to log of K2 over K1. Okay? So there's our ratio. We just need to say E to that power is equal to the ratio. Right? So this is what that's our unknown. And I get 3.55 to the nearest whole number, 4. That's why the answer is D. Okay. I almost fell for it, right? They gave us a K value, and I was chasing that car. You know, the dog that chases the car. You know, what's he going to do when he catches it? Probably get run over. But I was chasing that number, and then it dawned on me that we're looking for the ratio right here. The ratio is what we want. It doesn't matter what the number is. So the ratio of K2 to K1 is close to 4. It's really 3.55, which is a long way from 4, but the question said nearest whole number. Okay, that's number 18. Maybe I better not erase all that. I might need it again. Let's see what problems are coming up, and then maybe I'll erase it. Okay, my still keeps drifting on me. All right, so let me mark that one off. We've done 18. Now, 17, right? Let's go back up to 17. All right, we won't need this. I can erase that now. There we go. Okay, 17. Okay, we're given this set of data for this reaction. 2 dinitrogen pentoxide yields 4 nitrogen dioxide plus oxygen. And these are the data, right? We notice that N2O5 is disappearing, starts off with this concentration, right here, and then we lose it over time. So it's disappearing. We're measuring the disappearance of the reactant. The initial rate of production of NO2 for this reaction is what? How much of this is the very start? Right? So the temptation here is to say, okay, the starting rate of the reaction is difference in N2O5 divided by the difference in time, right? So we would say that one minus this one, which gives us a negative number, disappearance, divided by this one, or this one, minus this one. That would give us the positive time interval. But that's an average rate over the first 10 minutes, right? That's not an initial rate. The initial rate is instantaneous. Remember, on a curved slope, the instantaneous rate is the slope of the tangent to the curve at that point. And we want the curve, right, N2O5 times 0. Something like that. We want the slope of the line right there at time 0. Right? You can't get that directly from this data. Right? You need to do a little more work, actually. So, what do we need to do? All right. This particular reaction, we've got to determine whether it's 0, first, or second order. And then we have to get the K value. All right. So, to decrease the amount of time required, and in the worked problem right here, I've already done that, plotted it out. So let's skip that step. And on an exam, I would give you that information. I would say this is a first order reaction with this data, blah, blah, blah. So you could immediately go to the first order rate equation. So in that case, let's see. I'm going to have to erase this and make room. In that case, the first order rate law would be something like this. There. Okay. Now let's go back to the question. It's good to look at the question every now and then to see we're on the right track. What's the initial rate? Right. So eventually, we've got to access this expression. Rate equals K to the first order. Okay? So we need to find out what K is. And we do that from here. Okay? So in order to do that, you've already been given that it's first order. So you can use initial and final concentrations anywhere in the equation, because now this is a straight line. But we have to turn them into natural logs. So over how much time? Well, let's just use the start and the end of the experiment, 0 and 70. So over 70 minutes time, the initial concentration was 1.24 times 10 to the minus 2. And the final concentration was 0.15 times 10 to the minus 2. Okay? Now we just need to solve for K. Then we can put it over here and talk about the rate itself. All right? So I need to take the natural log of this and the natural log of that. So what I'm going to do is, when I find the natural log of this, then I'm going to subtract the natural log of this, because it needs to come over here. Plus sign here, negative sign there. So I take this one minus that one. So 0.15. And you can put that value straight into your calculator. You don't have to convert it to scientific. That's exponential notation. And then we'll take the natural log of that, and then we'll take this one, 1.24 exponent minus 2, and then we'll take the natural log of that one and change the sign. It's a negative value over here. It'll become positive on that side. And then we add it to this one, because now I've already changed the sign. So it's minus 2.112. Equals minus K 70. So K will be positive because that's a negative and that's a negative. We're going to take that negative 70 and put it over here and divide it into that one. Right? So it's a negative 2.112 divided by a negative 70. Is 3.017 times 10 to the minus 2. That's our K value. Goes right in here. Okay? So our rate law then would be 3.017 times 10 to the minus 2 times the concentration of N2O5. All right. So we've got our rate law in terms of N2O5, but the question is, what's the rate of production of NO2? Right? That's the rate of disappearance of N2O5. The rate of production of NO2 is what? Look at this. Well, it's not going to let me. Here we go. There we go. There's your 4. There's your 2. The ratio is for every 2 N2O5s that disappear, 4 NO2s appear. The ratio is 2 to 1. Right? So if the rate is this for the disappearance of N2O5, the rate of appearance would be double that. Right? So the rate of appearance of NO2 would be twice that value. 6.03 times 10 to the minus 2. Okay. Now, why did I do? I did that wrong, didn't I? There must be something wrong with my calculations here. Let's go back and check. All right, did I set this up right? N2O5. There, that's right. How about this one? N2O5 at the end. Okay. 70 is the time interval. The beginning is 1.24 times. Okay, that's set up right. Let's see if I did my calculations right. So what's the natural log of this one? Okay, let me write that up there. The natural log of this one is minus 6.502. And the natural log of that one is minus 4.390. So now I want to keep this one on this side, and that one becomes a positive. Positive, change sign. Minus 2,112. That's right. And this comes down here, minus K70. So K, just bring the K over here and leave the negative over there. Okay, that's inverted. Is it not? Let's see. 70 should be over here. No, that's right. Yeah, that's right. 70 comes over here to the denominator. 2.112, 70, divide. 3.017, 10 to the minus 2, that's right. 3.017, 10 to the minus 2. All right. So I'm checking to see what I did wrong. Oh. This is the rate. Did you see what I did? That's not the K. Oh, yeah, it is. It's the K. Yeah, that's the K. That should be right. Oh, all right. This is correct so far. I just didn't finish it. This is the correct K. But what's the rate? Well, we need the NO2. What's the NO2 at the beginning? Well, the NO2 is 0, so we can't do that calculation, right? 0 times that would be 0. All right. So here's what we have to do. We have to say the rate of disappearance here is 3.017 times 10 to the minus 2 times N2O5. Right. So that's the initial rate, and this concentration is 1.24 times 10 to the minus 2. 1.24 times 10 to the minus 2. Now here, so this one times that one is the initial rate of disappearance of N2O5. 1.24. So that's 3.74 times 10 to the minus 4. Okay. So that's the rate of disappearance of N2O5. So the rate of its appearance of NO2 is twice that. 7.48. All right. So the nearest one to that one in their answers is A. I hear no questions, so I'm going to go ahead to the next one. That was 17. So we're working backwards now to pick up the ones I skipped. Let's see, do I want to do 15? Or is there a simpler one? Yeah. Let's skip 15. Let's go back to number 2. I think number 2 would be a lot easier. There we go. There's 2. All right, so here's our reaction. And I am going to annotate this one a little bit. All right, so here's the overall rate equation. 2 manganetes plus 5, and that's oxalic acid, plus 6 protons, or hydrogen ions, yields 2 manganese, 2 plus ions, 10 carbon dioxides, and 8 waters. First thing you'll notice about this equation is it may be balanced for the reactants and products that are shown, but it's not balanced on charge, right? 2 minuses here, 6 pluses, that's a 4 plus difference. Well, no, the charge is balanced. I correct myself. All right, so now that the charges are balanced, then where are the cations, right? That's a standalone anion. We know that that doesn't happen. That's a standalone proton. That doesn't happen either. The things that are missing are spectators. They don't participate in the reaction. So that's why they're missing. All right. Okay. So in order to simplify this process, this is a method of initial rates. Right? Each one of these rows is a separate experiment determining a rate with these different concentrations. Notice that we only have reactants in here. This reactant, that reactant, that reactant. No products. Because at the initial rate, the beginning of the experiment, there are no products. And that's the way we design it. You don't want products for an initial rate experiment because the products can eventually start to produce reverse reactions. And then you get a complicated, let's see, what's the right term for that? You get a mixed order reaction because you got an order going one way and an order going the other direction. So for the overall reaction, we can't do that. Now you can deal with it when you're talking about mechanisms, but not for the overall reaction. And then this methodology, we need initial rates. So we're only concerned with reactants. All right. So in order to simplify discussion, I'm going to identify each one of these reactants with a Roman numeral. Each one of these experiments with a Roman numeral. All right, so I need a text. And then I'm going to say this one is Roman numeral 1. And this one is Roman numeral 2. And this one's 3. And this one is 4. Okay. And let's see if we can straighten this thing out a little bit. Let's see. I need my mouse. Yeah, that's not going to work. Select. Okay, I picked the wrong one. Sorry. So now I need to move this one over. Let's move it over here. And this one we're going to move over here. And this one here. And this one up here. Okay, so each one of these experiments is identified with a Roman numeral. And the reason I did that is so that we could discuss them. Right? Rather than having to identify every component in there, we just say experiment 1, experiment 2, experiment 3, experiment 4. So the idea here is to write the rate law for this reaction and leave terms with their unknown designators. And then we've determined those as we go along. So the first one, well, first thing we do is this is number 2. Okay. So we're going to have the rate is equal to a K value. And then the first reactant, which is manganate, to its order. The second one is H2C12O4 to its order. And the last one, protons, to its order. And that's your generic rate equation, the rate law for this reaction. What we have to do is from this experimental data, tease out the values here. And the question just says, what's the rate law in terms of orders? It doesn't ask you what the K is. We're going to calculate the K, right? Even though it doesn't say to, we're going to do that. But the method of initial rates is really a ratioing exercise. So look what we got. If we plug in this value for MnO4 and this value for oxalic acid and this value for H2 and this rate over here, then what's left? Well, the rate constant and the orders are left undetermined. So what we want to do is we want to pick 2 equations in which the concentrations of components don't vary for 2 of them. In this case, 2, because we have 3. Hold 2 of them constant and let the third one vary. And this is what you get. Okay, we're going to do it for the first one. Okay, we go from 1 to 2 on this one. And in the process, between Roman numeral 1 and Roman numeral 2, the concentration here stays the same, concentration here stays the same, and the rate changes. Right? So if we ratio those, and we ratio them in such a way that we try to get whole numbers out of it. Right? So we need the larger one on top. That's why we put Roman numeral 2 on top. So we're going to ratio 2 to 1. Right? So the rate for 2 is 8 times 10 to the minus 4. And the rate for 1 is 2 times 10 to the minus 4. All right. So now we have K and we have values for MnO4. Right? So for the second equation, the value for MnO4 is 2 times 10 to the minus 3. To the n power. And for the first one, it's 1 times 10 to the minus 3. To the same order. These guys don't change. This one's 1 times 10 to the minus 3. 1 times 10 minus 3 to the m and the m. And this one is 1 and 1. Okay? So, what do we get here? Well, over here, we get this one divided by that one is actually just 4, right? 4 times this one would give you that one. Okay? That's the same as that. Constant, remember, constants are constant for a reason. They don't change. So the constants cancel. This term cancels. They're identical. This term cancels. They're identical. So what do we get? We get 2 times 10 to the minus 3 to the n power divided by 1 times 10 to the minus 3 to the n power. So remember your math. This one to that power and this one to that power is the same as this one divided by that one to the n power, which is 2 to the n power. So 4 equals 2 to the n power. So what's n? N has to be 2. 2 squared is 4. So that goes up here. Okay, see the pattern? Now what we need to do is hold manganate and protons constant and let the oxalic acid vary. So which ones would that be? Right? Protons are constant between these two, manganate's constant here, and oxalic varies. So 3 divided by 2, because the values, if you do it that way, then you get whole number values. Right? So the oxalic would be 2 times 10 to the minus 3 here. Right? And this is still 1 and 1, right? So they cancel. And this one now becomes 2 and 2. Right? So they cancel. And K's always cancel. Now we have different rates, right? For the third one, we have 1.6 times 10 to the minus 3. And for, see, it's 3 and 2. And for 2, we have 8 times 10 to the minus 4. Right? So how do you divide that one into that one? Well, the easiest way is to make the exponents the same. Then they cancel one another. So if we make this one minus 4 and take that power of 10 over here, that makes it 16. 16 times 10 to the minus 4 is the same. So 8 into 16 is 2. Okay? Now we want to bring down these values. Right? So that's correct, only it's a different exponent. Now it needs to be m. Let's do away with that. Like m. Okay? So that would be 2 to the m power. So if 2 equals 2 to the m power, m has to be what? 1. M equals 1. Okay? So now we can say that's 1. You don't have to write the number in there, but we'll do it for clarity. Now we just got one more to go. So let's take that out, and this. These are going to change. These will change. Use 2 different experiments. Those are the same. These are going to change right here. Well, let's see which ones give us a variable proton. 3 and 4. Right? You got to change here, there to there. So we want to put 4 on top and 3 on the bottom. So what's the rate for 4? 1.6 times 10 to the minus 3. Same for the other one. Okay, K's are the same. Manganate's the same, 2 times 10 to the minus 3. That doesn't change. How about this one? That one doesn't change from there to there, right? So that one cancels. Right? And this one is 2 and 1, correct? All right. So now what we have down here erase that, is 2 to the L and 1 to the L. So that's 2 to the L. What's this one? That one divided by that one is 1, correct? What power of 2 will give you 1? Any number to the 0 power will give you 1. So this one is 0. Okay? So now we have our answer almost. There's a little twist. A little twist that can cause you to pick the wrong answer. Well, actually, I've set up the answer so that it's unlikely that you'll pick the wrong one, right? Because anything that's there, if it's there, it's to the first power at least. All right, so if you have, let's see, 2, 1, and 0, if you have 2, 1, this one would be 1 first power, so that can't be it. That term to the 0 power disappears. It doesn't matter what the concentration is. It only matters what the K is to give you the rate. Okay, so in that case, you keep this second order term and that first order term, and that 0 order term goes away, which is why the answer is D. Manganate to the second power, oxalate, oxalic acid to the first power, times K. Now I mentioned I was going to calculate what K is. We can do that too. So now that you have this set up, we can calculate K. All you need now is a rate, concentrations, and we can calculate K. In fact, we don't even need that term. We only need these two. So you just pick one of the experiments. Doesn't matter to me. Any one will work, right? Because K is a constant. So any experiment will work. So let's just do the first one then. So the rate is 2 times 10 to the minus 4. 2.0, no, just 2, times 10 to the minus 4 equals K. And then the concentration of manganate is 1 times 10 to the minus 3 squared. And the oxalic acid is 1 times 10 to the minus 3 to the first power. Solve for K. Well, what's this term? That one squared and that one to the first power. That's that number to the third power, is it not? Right? So if we say 1 times 10 to the minus 3 to the third power, anytime you raise a power to a power, you multiply them. So this would equal 1 times 10 to the minus 9. Okay? So this would be K times 1 times 10 to the minus 9 equals 2 times 10 to the minus 4. And then K is equal to this one divided by this one. Right, K stays here, that one goes over the denominator. So this will be 2 times 10 to the plus 5, right? Minus 4 minus a minus 9 gives you a plus 9. Minus 4 is 5. And 2 divided by 1 is 2. So 2 times 10 to the 5th would be the K value for this data set. It didn't ask for it, but while we're here, I might as well. Okay, that was 2. We're not going to do 1. So let me see if we got any others that we can do. Yes. We did skip. Let's see. We could do 7 or 12. Let me see which one. We've got an hour, so we could do both of them, actually. Yeah. Let me see. Which one would be the simplest? Let's do 12 first. I think it'll give us the least trouble. And of course, I'm reminded of what my father used to say. That's what you get for thinking. Okay. So let's, let me get my mouse back. Go down to 12. Oops, too far. One more scroll. There we go. Okay. So let's make room. That left-hand side's getting kind of messy, so I'm gonna try to keep it on the center board. What did I say? 12? 12. All right. Consider the reaction. 2 ozones yields 3 oxygens. And here's the proposed mechanism. All right, so the overall reaction is 2 ozones yields 3 oxygens. And we discussed that a little bit at the end of the lecture. When we were talking about catalyzing these reactions in the upper atmosphere, destruction of ozone. This reaction goes on, you know, all the time at any level of the atmosphere. It's only a problem in the upper atmosphere where ozone is produced in significant amounts by the action of ultraviolet radiation on oxygen molecules. And this is more or less a reverse of that process. But the mechanism is proposed in 2 steps. Right, so we have this first step where you get 1 ozone molecule in fast equilibrium with oxygen and an oxygen atom. And that oxygen atom is a free radical. It has unpaired electrons. It's extremely reactive. And in this case, it's an intermediate. And then the second step is the other ozone reacts with that free radical. Oops, excuse me. There we go. And produces 2 oxygens. Yeah. Okay. So does it satisfy the condition first, Well, there's one ozone, there's the other one on this side. Right? Got that. This one cancels that one. And 1, 2, 3, there. So that's a valid mechanism up to this point. Now, if we assume that the second step is the slow step, and that's sort of implied by the arrangement of the steps in the mechanism, right? When they put these types of double barbed arrows in there, they're saying that that's a fast equilibrium, right? It happens so fast, it's just, there's a balance there. So this is the slow step. All right. So we should be able to write a rate expression for this reaction based on the slow step and the molecularity, right? The molecularity here is 2. And what it would do is it would give us the rate is equal to this one to the first order times this one to the first order, and then our K. Right? So that would be a valid, well, an almost valid rate equation for this reaction based on the slow step. There's just one problem. That O is not in the overall equation. It's an intermediate. So we got to get rid of it somehow. So how do we do that? We turn to our fast equilibrium. So let me put this one over here so I can use that space. So if this is our beginning rate, I said I wasn't going to use this space, but I have to. O3 and O. All right. So now we're going to use this one. All right. So what does a fast equilibrium mean? Well, if this is K1, actually, shoot, I shouldn't have erased that. Let's put the second one over here is O3O, O3 plus O equals 2O2. This is K1, and this is K minus 1. It's the reverse. Right. So the forward reaction has a rate constant, and the reverse reaction has a rate constant. And then this one has a rate constant. Okay, so what can we say about this one? Well, in order for it to be equilibrium, and we're going to discuss this in more detail in the next chapter, in order for it to be equilibrium, the rates of forward and reverse reactions must be equal. Right? In order for them to balance, they have to be occurring at the same rate. So the rate this direction would be what? Rate of O3 that's the expression for the rate of O3 is equal to the reverse, K minus 1 of O2 and O. Right? That rate's equal to that rate. So now we'll just solve for this one because we need something in terms of reactants and products, reactants and or products that we can use to insert into this and get rid of that O. So if we solve for this one, right, it puts that one over here and this one over here. Right? I just brought that term over here. Now it's equal to that one, and I just flipped them. So now we have this value that can go in here. So this rate now becomes this K and this expression, K1, O3, and K minus 1, O2. Okay? So now, let's see. Actually, this is K2, right? Because it's based upon this one right here. So now we just bring all our K's together. Let's do it over here. Bring that over here. Rate equals K2, K1 over K minus 1 times what? O3 squared. O3 times O3 divided by O2. Okay? These all the constants, those variable constants, are equal to, or they're combined into, a single K value. So then the rate becomes this K here times this one squared and this one to the minus 1, because it's in the denominator. So if we bring it up into the numerator, the exponent changes. So that's what you're looking for in your choices. Rate equals K times O3 squared times O2 to the minus 1. That's why the answer of 12 is C. All right. So that was 12. And we still got time. So we could look at 7. We could look at 7. All right. And that should finish it out once we get through with 7. By the way, when you took your first exam, rumor has it that once you got into lockdown browser, you don't have access to any of those extra materials that are in that folder. So from now on, you'll have to print a copy, keep a copy of that useful information in the folder that's with the exam before you go into lockdown browser. Once you get into lockdown, then you are locked out. But anything that's in the review document, useful information is valid. You can keep that with you during the exam. And in this case, that includes this big table full of formulas and the polyatomic ion table and a periodic table. You always need a periodic table. I don't know how people get along in their daily lives without a periodic table next to them. Explains a lot of the troubles of the world. Okay, number 7. Let's see, how much space am I going to need for this thing? It's going to take some doing. Let me just start over here on the left then. And be sure I'm centered. Okay. That's not 7. One more. There we go. Okay. This is going to be taxing, mentally taxing. We're given the reaction 2 nitrogen monoxides plus 1 oxygen yields 2 nitrogen dioxide. And it says that the rate law is obeyed as the disappearance of oxygen, the measured disappearance of oxygen, is equal to an observed K value times nitrogen monoxide to the second order times oxygen to the first order. Now that's, like I said before, that's coincidental. The fact that this is second order has nothing to do with that too. It may have something to do with the mechanism, for sure, but that's it. All right, so how do we approach this? Well, of course, first of all, we have to determine which, if any of these, do not satisfy the first condition, right? You have to add them up in order to obtain the overall equation. So this mechanism's steps must add up. So let's see. How about the first one? Let's see, 2 NOs, right? There's 2 NOs right there. That's good. And then there's an N2O2 intermediate that cancels on the second step. That's good. Then there's 1O2. That's good. And there are 2 NO2s. So A is kosher, so to speak. All right. How about the second one? There's 1 NO. There's another NO. Okay. There's an O2. That's good. There's an intermediate that disappears here. And then there's 2 NO2s. So that one's right. How about this one? 2 NOs. Okay. And then we have an intermediate, and an intermediate disappears there and produces 1 NO2 plus another intermediate. That intermediate O disappears with this step. That's good. Then we get another NO, which produces a second NO2. So that NO, that means there are 3 NOs. So C can't be right. Right, so we can throw C out because there should only be 2 NOs. There are 2 here. We got an extra one here. Right? Does that make sense? It should. Unless there's something I'm missing. Yeah. So we can throw C out. How about D? All right. There's an O2. There's an O2 produces. Well, that doesn't make any sense at all. Right? What value is a slow step that takes in reactants and spits out the same reactants? So D is just stupid. I mean, I won't call people stupid to their face, but D as a proposed mechanism is just dumb. So we've eliminated C and D. We just need to focus on A and B. All right. So let's do that. For A, the slow step is the rate determining step, right? So NO plus NO equals N2O2. NO plus NO yields N2O2. That's the slow step, right? So the rate expression should be the rate equals K times NO to the second power. Okay? And since NO, right, we haven't muddied the water with intermediates. The problem here is, where's the O? Where's the O2, right? Because the observed rate law is here. O2 needs to be there, but it's not. And there's no way to get it in there because we don't have an intermediate that needs to be substituted for. So that means A doesn't satisfy, right? So let's just look at B and see if it does, because maybe B doesn't either. And one of the choices you have is none of these, right? Maybe none of them work. So let's look at B and see if it satisfies. So B, the rate determining step for B is NO3 plus NO yields 2NO2. NO3 plus NO yields 2NO2. Is that right? Yeah, that's the slow step. Okay. So the rate expression for this one would be some K, NO3, and then NO. Right? Okay. So this one gives us a problem. It's got one NO in there, which is not enough, but it's also got an intermediate that we have to get rid of. Right? So we're going to have to go back to that trick where we have, we look at this fast equilibrium. NO plus O2 yields NO3. Actually, it's a fast equilibrium. Right, NO3. Yeah, that's right. So now we've got this K here, which we're going to call, since the, where am I? Yeah, since the fast equilibrium is first, this is going to be K1, this is going to be K2, K minus 1, reverse reaction. This is going to be, nope, yeah. This is going to be K2. Right. So this is K2. So the expression here is the same as before, where we had balanced forward and reverse reaction. So this forward reaction, NO and O2 times K1 is equal to K minus 1 times this one, NO3. Okay. So we just need to solve for that one, right? NO3 is equal to K1 over K minus 1 times NO and O2. Now we can substitute this in there. So that gives us the rate equals this term fits right into the O3. K1 NO and O2 divided by K minus 1, and that's times NO. Right? So this term went right in here between that one and that one. So now if we combine this one into a K, we combine this one and this one into NO to the second power, and that leaves us with oxygen. That one gives us something resembling the experimentally determined rate law. NO to the second power, O to the first power, and a K. So that means that B satisfies the conditions, right? That's a long way around, and we had to make some assumptions and eliminate some ridiculous ones. But in the end, that's the only mechanism that makes sense, and that's the way they do it in real life, right? They take these proposed mechanisms, they spit out as many as they can, and my guess is these days they have computer programs that will help them generate possible mechanisms. But it's such a specialized program that, you know, people like us don't hear about them. But my guess is that once you get on the inside, they've got helpers, electronic helpers. And then you still have to do some thinking, of course, to eliminate the impossible situations. All right, we're done by about a half hour early, I think. I'm checking my marks to see if I've got anything that we've missed. All right. No, we're good. Oh, you might see, I noticed one error in the useful information. When you look down at this, let's see over here, down at this very far right corner, you'll see that the integrated rate, the integrated Arrhenius equation is missing a 1 in the reciprocal of T2. Right here. There should be a 1 right there. So don't let that fool you. Don't think that's right. That's wrong. And my guess is I haven't corrected it. If it's there. If it's not there, then you can ignore that statement. Oh, I did mention the possibility that I would show you how the half-lives were derived. Maybe we'll do one of them. Just so you can see that they weren't just pulled out of thin air. Let's try, let's see, how about, nah, that one's gonna require calculus. Let's try, oh, no, okay. Right. The integrated rate law does require calculus to take the differential rate law and make the conversion. But once you have the integrated rate law, then you can derive the half-life. So if we derive the half-life for, let's say for the second order reaction. So for the second order, you would have 1 over concentration of A equals positive K times T plus 1 over A 0. Right? So what does the half-life mean? The half-life means that this concentration is equal to half of that one, right? After a certain amount of time, right? After that amount of time, then this one is equal to half of that one. Right? That's your beginning. So after this amount of time, it's equal to half of that. So what if we substitute, since the half-life is based upon a beginning concentration of some sort, then we need to get rid of this one, right? We want to know what's the beginning concentration. So what we would do is we would solve this one for that A0. See, I need another marker. Let's see if this one will work. So this one divided by 2 is equal to this one. Okay? Now if we substitute this term, oh, excuse me, that's not right. We want to substitute for that term, right? So we just take this one and put it right there because it substitutes for this one. So 1 over A0 divided by 2 is equal to K T. Now we're looking for T1 half plus 1 over A0. Okay? So what is this one? Well, the denominator of the denominator is the numerator. So this one is actually 2 over A0. And then we can also subtract this from both sides. Minus 1 over A0 is equal to K times T1 half. Okay? So now, what is this term? Well, 2 minus 1 is 1. Right? So this term reduces to that term. And then this term becomes that K comes over here into the denominator. Okay, so there's your half-life for the second order reaction. That's why it's like that. And you can do that same process with the other two, if you're so inclined. Well, let's see. We got maybe 15 minutes left. So I'll open the floor for any questions you might have. This is the one. This is the one problem I left out, and I wanted to present to the class. And it's just, I'm just going to make up values so that we'll have something to look at. So if we have our component A, and we have the data, of course, is set up with time, and then A, and then log A, and then you could do reciprocal of A, you know, and get all that data. And you plot time against A, and of course you get a curve, right? So that can't be it. So in this case, we plot log A against time, we get a straight line, right? So all straight lines have a fairly uniform equation based upon the data points. And we would get something like this value, and that would be equal to a minus K T, right? Minus is a negative slope. Positive slope would be this way. This is the negative slope, plus the natural log of A0. And this would be right here, a log of A0. Right? Y-intercept. right there. And the slope here would be a negative k. So if you have a value for that equation, let's just say it's something like, I don't know, if the equation were reported in terms of y and x, let's say we have a y equals a minus 3 times 10 to the minus 2 x plus, I don't know, 7 times 10 to the minus 3. So if you have that equation defining this line, you know that this right here is equal to negative k. So what's k? K is this term right here without the negative sign. So if you know the slope of the line, you can find k very easily. If you need to know the y-intercept or the a0, then you just look for its intercept here. Now that's the log of a0. So you would have to make the conversion to find out what actual a is. Okay? So if this were it, and that's equal to log a0 is equal to this, then a0 would be e to the 7 times 10 to the minus 3. Okay, so when you're interpreting these graphs, you got to remember that there was a transformation that was used. So if you need to find the raw information, you may have to do a reverse transformation to get the data. Okay, so if you have this equation defined for that line, that equation gives you lots of information. If this were second order and that were 1 over a, then the slope would be the other direction, right? This would be a positive value of k, and then you would just read the slope straight off the line would give you the k. And any other calculations, you'd have to take the reciprocal of them to back figure, like I did here, to back figure to the a value. Okay. Now, if it were 0 order, you just get a straight line right off the bat, and then you wouldn't have to do any transformation. So that's the point I wanted to make. If you see this plot here, like that, what order is this equation? First order. Natural log means first order. If it happened to be a reciprocal, second order. If it's raw data, and you still got a straight line, of course, then it's got to be set to 0 order. So that's an easy answer there. Just looking at the way the plot's constructed. And then the rate constant. So those are 2 basic information. Actually, you can get 3, because I talked about the y-intercept. You can glean a world of information from a graph. Okay, that's all I wanted to do. That was the one problem I missed discussing during our lecture, and I'm going to tack it on the end of that lecture and send everybody an email so they'll be sure and know that it's there, because this type of question might pop up on the exam.
Oh.